Okay, so I put these in some order of increasing difficulty. And this one actually doesn't even ask you to give a reason of what you're going to do, but we'll get in a good habit of putting that down as we go. So this first one here, what we're looking at is clearly a diameter so I know that if I've got an angle in a semicircle, if it's a diameter, it's a semicircle, then this angle is a right angle. So I know that that angle there is 90 degrees. So all I have to do is to do 180 less 90 less 28, and that will give me the size of angle X. So in doing that, I get, that's the same as 90 less 28, which is 62 degrees. So the reason angle in a semicircle is a right angle. Okay, so that's the reason. It's not asking for it, so you wouldn't get penalised if you didn't write it, but let's get in the good habit. Okay, the next question has got a greater tangle of lines and tangents and so on. So what have we got? We've got 3 points A, B and C, A, B and C, lie on the circumference of a circle centre O. The tangent RS meets the circle at A. So I've got a tangent, I've got a diameter, and I've got a pair of lines firing off the diameter. So I can spot straight away that that there is going to be a right angle. And the first thing that they want me to work out is angle ACB, which is what we've just done. So angle ACB is 90 degrees. This time we've got to give reasons for our answer. So angle in a semicircle is a right angle. So that's that one done. The next one that they ask us to work out is angle ABC. So I need to find this angle. Now what I can also see there are two ways of doing this. I'll show you both ways, but probably the way that I would have spotted it myself as a student would be, I've got a radius, I've got a tangent, so I know that that angle there is 90 degrees as well. So I could say that angle OAR or OAS is 90 degrees. Okay, so angle OAR equals 90 degrees, angle between a tangent and a radius. Which means that angle OAC is 90 less 62. So OAC is 90 degrees less 62 degrees, which is 28 degrees. And then I've got angles in the triangle. I know that that there is 28. So angle ABC equals 180 less 90 less 28, which is 62 degrees. Angle in triangle equal 180. So that's one way of working that out. First of all, spotting, you've got a tangent and a radius, 90 degrees. It's an easy one to spot. So I can work out that missing angle in the triangle. then I've only got one unknown. But the other way of doing it is you can spot it straight away by that alternate segment theorem. If I just come back and turn that around, you can see there that that angle and that angle are the same as that angle and that angle there. So you could just write it down if you spotted the alternate segment. Okay, so or, and you wouldn't, obviously you wouldn't do it both ways in the exam unless you had plenty of time and you wanted to show off. So or angle ABC is the same as angle RAC equals 62 degrees, alternate segment theorem. Okay, so there's two ways of doing it. That angle there is the same as that angle there, or the longer way but probably the more logical way of working that one out. Okay, so the next one what we've got here first of all then is BOC. Well, we've got the makings of the arrowhead going on here. I just pull back this one. You can see here the angle subtended at the center is twice the angle subtended at the circumference. So exactly the same here. Here's our 2 points. If we're firing to the center and from the same point out the circumference, that angle is going to be twice that angle. So BOC is twice BAC equals 26 times 2, 52 degrees. And giving reasons for your answers again, so you'd have 1 mark for that. So the reason is angle at center is twice angle at circumference. Okay, so you don't have to write it perfectly, just so long as you're showing the examiner you're using the right theorem. And then DCT, so this is the angle that we need. Okay, now what we have here is we know that this is 52 degrees. We've got a parallel line going on, so if that's 52 degrees, this angle in here is also 52 degrees, because we've got alternate angles on a pair of parallel lines. And also we can see that OC is a radius which touches the tangent, so I know that this angle here is a right angle, which means OCT is also a right angle. So if I take 52 from 90, it'll leave me that angle there. So just to write that down then, so BOCD, so angle OCD, go from O to C to D, is equal to angle BOC, which is equal to 52 degrees, and that's alternate angles in parallel lines. Then I know that OCT is 90 degrees, angle between radius and tangent equals 90 degrees. So angle DCT DCT is going to be 90 less 52, which is DCT 90 less 52 is 38 degrees. Now, if you just written down 52 and 38, you would still get 2 out of the 4 marks. Okay, so don't think, oh, I can never remember that, therefore there's no point trying. You're going to get at least, half the marks are going to be for the actual angles that you've established. Okay, so the next one, I can spot straight away there now that this is going to be one of those wonky Z-angle type things, or alternate segment theorems as they're properly called. So if we just pull up the one that I drew earlier and see if I can fit that on, that's pretty much what we've got. Okay, so you can see there straight away that angle X, that 68 there is going there, and that 46 there is going there. So we can plonk that straight in and see what we need to work out. So they want us to find TRS. So TRS is 68 degrees. And you can just write down alternate segment theorem. So that was alright. We can trigger that straight off. Okay, so the next one. So what we've got here, 4 points A, B, C and D lines, circumference of a circle. Right, nothing is going through the centre, so we can't assume that we've got a diameter there. We can't assume we've got any radii there. Okay, so don't assume anything. But we do know that AC and BD intersect at the point P. Given that BAC is 32, and DPC is 134, find the size of ACD. ACD, giving a reason for your answer. Right, so that's the angle that I need to find. Now, the theorem that I'm going to be using, I just shuffle my bits of paper. Is this one. Right? Angles subtended by an arc in the same segment of a circle are equal. So that's saying that what I'm bouncing from B up to that part and back to C, and that one B up to that part and back to D, there's my segment. Okay, so it's like turning this around. Okay, so I've got AB, they've got BC. These ones up here are all the same. So that angle there is 32. It means that this angle here is 32 as well. Once I know that that's 32, I've got 2 out of the 3 angles in my triangle, so I can use the angle property to find the missing angle. So what we're going to say there is that angle BDC is the same as angle BAC, which is 32 degrees, and that is the angles in same arc, same segment are equal. So angles in the same segment are equal. Then angles in a triangle, so one we're trying to find is ACD, which is going to be the same angle as PCD, which is going to be 180 less 134 less 32 in that triangle, and that comes to 14 degrees. Angles in triangle equal 180. Next one, again, hopefully this triggers now straight away your wonky parallel line idea. I'll bring it back in. There it is. So that's 80, that's 80, that's 60, that's 60, alternate angle. Sorry, alternate segment. Right, so we bang those in straight away. Find the size of FEG. We've done it. FEG is 60 degrees, alternate segment theorem. Okay, so let's take a look at this one. Okay, I'm in the zone as far as alternate segments are concerned, so I can see that here I've got my alternate segment. So if that's 58, this up here is going to be 58 as well. Now I don't know whether I'm going to need it yet, but I'm going to bear that in mind straight off. If that's 58, wonky parallel line, that's 58 there too. Anyway, let's take a look at what we've got here. So we've got the reflex DOB. So DOB is this angle here, but in order to tell me whether I need that side of it or that side of it, it's telling me that I want the reflex side, which is greater than 180. So the angle that we were looking for there is that one. Now, there's two ways we can arrive at that. The quickest way is if you spot, let me go back to my earlier drawings. We had this earlier with the arrowhead going that way. Angle subtended at the center is twice the angle subtended at the circumference, but we also had that form of it. Okay, now if you look at what we've got here, that's exactly what we've got there. That we're going from these 2 points B and D, we're bouncing out to the circumference and back again, and then from the same point to the center. So if that's 110, that's double it. So we can write that down straight away, that DOB is 2 times 110, 220 degrees. And the reason for that is angle subtended at center, angle at center equals 2 times angle at circumf. Okay, so again I'm shortening that down. Angle at center is 2 times angle at circumf, but you know, the examiner knows exactly what I mean there. Now if you didn't spot that, the other way you could have got to the same thing is a longer way, but again it might be more logical to see. What we've got, ABCD, is a cyclic quadrilateral. So that angle and that angle must add up to 180 degrees. So this is going to be 70. Okay, so the alternative, or BCD is 180 minus 110, which is 70 degrees. Op ang cyclic quad. Then we've got the arrow that is easier to spot. So if that's 70, that is 140. Okay, and that's the obtuse DOB. So it's the same reason as that. Your angle at centre equals twice angle at circumf. And then to work out the reflex, you would take it away from 360. So reflex DOB would be 360 less 140, which is 220 degrees. Angles around a point, 360. So it's more work that way, but it might be easier in those stages for you to see what to do. The sort of that version of angles are less easy to spot than that version of angles. And then BDC, right, so with BDC, what I'm working with here, BDC is that angle there. Now, as I said earlier, I was on a roll with my alternate segment theorem, and I knew that if that's 58, this up here is 58 too. So I've got two angles in that triangle BDC. Okay, so I'm sorted. Where am I going? So I'm going to write down that CBD equals 58 degrees. Alt seg theorem. So in triangle BDC, I know two angles. Angle BDC will be 180 less 70 less 58, which is 52 degrees. Angles in triangle equals 180 degrees. So that's the way into that one. There are other ways into it, but that is by far the easiest way. I mean, what you could have done is you could have taken those two away from 180 to get that part of the segment, and that will then bounce off the alternate segment theorem to give you that straight away. So that's another way of getting there. Okay, the remaining questions in this little bundle are algebraic circle theorem questions. As if it's not bad enough to give you these with numbers in, sometimes they'll give you them with letters in, and you have to work them out algebraically. So this one is a tangent one, which looks like the one that I drew. It looks like that. So what you're spotting here is that AQ and BQ are equal in length, and that if we join OQ together, we get two identical triangles, two identical right angle triangles, because that's a tangent to a radius and that's a tangent to a radius too. So if we split that up to get my two identical triangles, and it's telling me that given that AQB is 2x, which means that this angle is x and that angle must be x because they're identical. So angle AOQ, which is this angle here that we're trying to find then, it's in a triangle. I know that angles in a triangle add up to 180, and I know that that's 90. So taking those away will give me that. So angle AOQ so triangle AOQ is the same as triangle BOQ, because the lengths of the tangents are equal. And angle AOAQ and OBQ are both 90 degrees. And the reason for that is tangent to radius equals 90 degrees. So we've established that they're identical triangles. So angle AOQ will be 180 less 90 less x, which is 90 less x. So that's your answer. That's AOQ in terms of x. Okay, this is another angly one, algebra one. Now we should be pretty hot on the alternate segment here. If that is x, bouncing back, that is x. I'm also seeing that this is an isosceles triangle, so these two angles at the bottom here are the same. So let's just write this down as we go. So angle BAC is equal to x, and the reason for that is alternate angle theorem. Triangle ABC is isosceles, so angle ABC is equal to angle ACB, which is equal to 180 less that divided by 2. Which is the same as 180 divided by 2 less x divided by 2, which is 90 minus a half x. So you've proven that, you've got your reasons. Alternate angle theorem is the reason, isosceles triangle is the reason that you can do that. And then the final question, again, is a nasty algebra question, but if we see what we've got here, I can see an arrow, so we're going to go that way, or we could be going that way, depending on what they want us to work out. So they want us to work out angle ABC. So ABC, so we can see the arrow clearly there. So ABC is half of AOC. A half of AOC, so that's 3x. And the reason for that is the angles how do I write the thing down? Angle at the centre is angle at the centre is twice angle at circumf. And then the final one, ADC, is that one there, and I'm in my cyclic quadrilateral now, so that is going to be, or that and that are going to add up to 180, so that is going to be 180 less that, which I've worked out to be that there. So ADC is going to be 180 less 3x. Opposite angles in cyclic quad add up to 180 degrees. And that's pretty much it. So watch out for the alternate segment. If you're lucky, you'll get questions with numbers in. If you're unlucky, then make them algebraic. But as long as you can spot and somehow try and remember the words, but if you can't remember the words, just writing down the answers will get you half marks.